game ones?
Nope, sadly no games for them.
Can you make up a game for these?
I guess I could make up a game for them, but we're just gonna go with the worksheet.
Are these just as easy or not?
They're not any harder. They're just a little bit different. So let's see. All right, first things first. Notice that our fulcrum is not in the middle. Okay, so we're starting with first class lovers, like I said. Also, side note, because we have 2 online days this week, yes, Thursday and Friday. So I was planning on giving you a worksheet either today or tomorrow. I'm going to move that to Thursday or Friday, and you're going to get an assignment on Thursday and another assignment on Friday. Got it? Okay. Yes, it's going to be over levers. I mean, it shouldn't be very hard. What? So the one I assigned Thursday morning at 8 a.m. will be due Friday at 2. The one I assigned Friday at 8 a.m. will be due Monday at 2. Yeah, so it'll be your standard, what we're supposed to do on when it's assigned, when it's due.
So is like one of them going to be the first class and the other one
They're probably all going to be levers. We might, by that point, have gotten to like inclined planes and stuff, so there might be some inclined planes thrown in. So, yeah. Anyways, we have a lever here. Okay, notice, like I said, the fulcrum is not in the middle. Good? Now, if we were to push on this side, how is our lever going to behave? Are we going to be able to lift heavy things with it? Probably not, right? So why would we want to push on this side when it's way closer to the fulcrum? What would that make, do you think? It's one of people's favorite things that levers are made, or levers are.
Catapult.
A catapult, okay? So if we push on this side and our force, the thing we're lifting, is over here, we don't have to move very far over here to get this to move a big distance really fast, okay? So this would be very much like a catapult. Our classic first class lever catapult is actually a trebuchet, okay? So we will talk about that. We'll see. I might have a video assignment on that maybe. I think I'll wait till we're back in class. Probably not online. We'll see. Anyways, so this would be a catapult. Okay, now if we go the other way, let's say we're applying our force here. Okay, is this going to make a good catapult? No. Okay, what's it going to be good at? What was the thing I asked with the catapult before? Yeah. It's going to be good at lifting heavy things. Okay, so because we have that trade-off that we talked about with our force times distance, here we're going to have a big distance, right? So we won't have to apply as much force to lift something heavy up over here because we've got a smaller distance over here. Make sense? Any questions? Okay. All right. So let's actually do a problem with this. Okay. Do you want to do a catapult or lifting something heavy?
Catapult.
Okay. All right. So let's say we have a reasonably small rock. Okay. So a kilogram is going to be about 10 newtons. So let's say we have a half a kilogram rock. We have a 5 Newton rock here. Sound good? Yeah? All right. What distance do you want it away from the fulcrum?
20 feet.
Let's keep it in meters.
20 meters.
20 meters? That's pretty long, but we'll go with it. So we've got 20 meters here. And then how far is our force away from the fulcrum? It should definitely be less than 20 meters.
3.
3? Okay. 3 meters away. Now, what we want to find out is what is the minimum force we can apply to lift this. Now, for something like a catapult, we're probably going to want a significantly larger amount of force there because we don't want it to just balance. But this is going to be the minimum force we can apply to lift that 5 Newton force. Good? Okay. So this is our force. Why don't we call it side 1? So we want to use the force times distance equals force times distance equation. We don't know our force here, but we know everything else in this equation, right? Yeah? Okay. One thing I want you to remember with levers, this is really easy to do with first class levers, a little tiny bit harder with second and third class levers. The distance that goes with each force is going to be the distance it is from the fulcrum. Okay? So on first class levers, if it's on this side, it goes together. If it's on this side, it goes together. Good? Okay. So we have our force 1 times our distance, which is 3 meters, equals our force 2, which is 5 newtons, times our distance, which is 20 meters. Any questions on how to put those in there? No? Okay. So, what's 5 times 20? Right? You guys not awake yet? All right, so we've got 100 on this side. We've got 3 on this side. We want to move the 3 over to here. So we're going to divide both sides by 3. That'll cancel out the units of meters. What's 100 divided by 3? It's not going to be even.
33.
Yeah. I'm going to put it over here. Okay, so we get 33.3 newtons. Everybody good?
Yes.
Any questions on how we did this? No. So with a catapult, we have to apply a lot more force to be able to lift something even as small as half a kilogram. Okay? Good? Now, like I said, this is not a huge amount of force. This is about probably 3 kilograms or so. 3.5 kilograms would be enough to lift this. So this isn't a huge amount of weight, but it is still much larger than our half kilogram rock. Cool? Now, when you get to things like full-size trebuchets and stuff, a lot of times that counterweight is several tons. Because however much your force is unbalanced there, adds to the speed of how fast it gets going. Cool? Any questions? No? All right. So our first class levers, we've done quite a bit with them. For those of you online, if you have not played with the simulation, you should definitely go do that because that's going to give you a lot more practice on this. Everybody in here good? Okay. All right. Let's go on to second class levers. You guys remember what second class levers we're good at? What was it? You don't remember?
They lift heavy things.
They're good at lifting heavy things. So with our second class levers, our force that we are applying is always going to be applied here. So we'll call it F1 just like we did on our first class lever. Okay? The load or the thing that we're lifting up is always going to be closer to the fulcrum. We'll call that F2. Everybody good? Okay. Now, our distances from the fulcrum are still the distance that force is from the fulcrum. They're just both going to be on this side because both of the forces are on this side. Does that make sense? So this distance from the fulcrum to force 1 is our distance 1. And this distance from the fulcrum to force 2 is distance 2. Good? So as long as you can keep it straight that it's the distance from the fulcrum to that force that goes with it, it's not that hard. But some people have a little bit of a harder time keeping these separate because they are both on the same side of the fulcrum. So just be careful with that. Good? Any questions? No? All right. So a great example of a second class lever is a wheelbarrow. Okay? So with our wheelbarrow, a lot of times wheelbarrows are what, like foot, or not a foot, a meter, meter and a half long. Does that sound reasonable? Says a meter? Yeah. So generally they're a meter, meter and a half long. Let's see if I can draw a wheelbarrow. Haven't drawn one in a while. All right, so there's our wheelbarrow. Okay? Our fulcrum is going to be our tire. Yeah? And we're going to have something in our wheelbarrow. What do you want in our wheelbarrow?
Dog.
A dog?
No.
Not a dog?
Mine goes.
A goat? You want a goat in there?
Yes.
Okay. See if I can draw a goat. Sorry. Our goat's probably going to look fairly like a dog. That's generally what happens. I don't think that made it better. That's not looking very goat-like, is it? Well, part of it is this. That's at least somewhat better. Is the nose part like too long?
I think it's fine. I think the thing is, for me, the thing is it's sitting down.
Yeah,
My goat
goats
never
never
sit
sit
down.
Fair enough. That is fair enough. Okay, so our goat is, for some reason, sitting in the wheelbarrow. It's probably why it's in the wheelbarrow is because it's sitting down. That's weird. Anyways, so we have our goat in our wheelbarrow. How heavy is our goat?
Heavy. It's heavy.
We know.
So I would prefer it. Well, I guess we could do it in pounds because we'll just get our force that we apply in pounds. A 30-pound goat. Okay. So our goat is 30 pounds. Okay. How far is the goat from the fulcrum?
It's like a reasonable.
So I mean, if our whole wheelbarrow is probably 1.5 meters, you're probably, I don't know. I'd say anything less than like 1/3 of a meter would be completely reasonable. or 1/3 of a meter. So like
Something like that.
0.25.
Yeah.
So we're going to say that the distance from the fulcrum to here is 0.25 meters. Okay? Then we need our distance from here to our hands. Okay? So do we want meter, meter and a half? Just a half a meter?
Wait, meter and a half. Oh, meter. Oh, okay, meter to.
What do you guys want? Are you too tired to make decisions this morning? Okay. Let's go with a meter and a half. That'll make our advantage a little bit better. Okay? So what we want to know is our force here, or what we have labeled as force 1 on this picture. Good? Any questions? No? All right. So our equation is still force 1, distance 1 equals force 2, distance 2. Okay? So our force 1 is going to be the weight, or I guess our force 1, sorry, is our force that we're applying. Okay? Then we need that times our distance, which is our meter and a half. So that's our side that we're applying. So our distance and our force. Then the other side of our equation is going to be the goat. Okay, so the force from the goat is 30 pounds. And then our distance is 0.25 meters. Good? Anybody not know where I got all the numbers from? No? You guys are good? Okay. So, on this one, we're going to do it a little bit faster. If you want to be able to just stick it in your calculator one time, what you're probably going to want to do is divide by this first. And then just stick 30 times 0.25 divided by 1.5 into your calculator. So now we can just stick this all in our calculators at one time. Do be careful and make sure that it actually has the 30 and the 0.25 on the top, and then you divide by just the 1.5. Good? You should get your calculators out. Yeah, it is 5. So, because of the way this works out, this ends up feeling like we are lifting something that is 5 pounds when we're actually lifting up something that is 30. Good? Any questions? No? All right. So that's how you do second class levers. They're really not any harder than first class levers. It's just that you need to be careful to keep your distance with that force. Good? Any questions? No? All right. So next we should do our third class lever. So our third class lever has the same base, but we switch our load and our effort. Okay? So, should we switch it up even more this time and actually solve for our distance? Yeah? Okay. All right. This time, we are talking about a third class lever, like I said. Our force that we are applying, what we've been calling force 1, it doesn't have to be force 1, but what we've been calling force 1 is over here, closer to the fulcrum, and our force 2 is farther away. Good? Yeah? Our distances, once again, go with the force that we are talking about. Okay? So we have distance 2 goes with force 2. Distance 1 goes with force 1. Everybody good? Any questions? No? Okay. So, in this case, we are going to have a whole bunch of things like baseball bats, golf clubs, catapults, things like that. We're going to have to apply a pretty big force, but this end is going to get moving pretty fast. Sound good? All right. So what do we want to have as our lever this time? Do we want a catapult?
Yeah.
Yeah? Okay. All right. See if I can draw a reasonable catapult. All right, so this is our bar that's going to stop our arm and fire off our thing. This is our base that sits on the ground. This is the rope that's holding the arm down. Okay. What are we firing in our catapult? Are we firing like giant boulders or something like that?
Okay.
Something really big?
Yeah.
Cows.
Cow. Do a cow.
One
Do two of
cow.
them.
I'm just going to do one cow.
Like the mighty butterfly.
The cow is looking better than the goat, which is probably good. All right, there's our cow. It's on the catapult. Okay. How heavy is our cow?
Heavy.
Uh,
1,000 pounds.
4,000 pounds?
2,000.
2,000?
fine.
Okay, so our cow is 2,000 pounds. That's our force going down. How far is the cow from our force, which is going to be applied pretty darn close to our fulcrum? So how far away is the cow? AKA, how long is this board? 10 meters? We got a 10-meter lever arm. And then our force is going to be applied right here. I'll say, we'll go like that. How big is our force going to be this time? Hint, it probably should be bigger than 2,000 pounds.
5,000.
5,000? Okay. So we've got a 5,000 pound force here. And what we're going to be looking for is our distance. I guess that's distance 1. That this is going to be away from here. Once again, this is going to be our minimum distance. If we made it closer to over here, then it would actually fire the cow faster. Cool? Any questions? Okay. So we'll set up our equation once again. This time we know our force 1. It's 5,000 newtons. Then our force 2, 1,000 pounds, times 10 meters. Good? Yes.
So where's one at?
Distance 1 is this distance. It's really small because it goes from where our fulcrum is, right here, to where our force is applied. Good? Okay. All right. So we get yes. All right. Quick way of doing this. You can cancel out the zeros as well. Okay, so you end up with 20 divided by 5, which gives us 4. Good? That's a nice shortcut. So this means that our force is actually like way over here, right? And that's just to lift the cow up. That's not really to fire the cow off. Okay, so if we know we can only apply 5,000 pounds, we might want to fire something a little cow, either that or move it over this way. Okay? Now, the other option we can do is to start flying here, right? So if we added another 0, we had 50,000 pounds instead of 5,000 pounds. We then have another 0 we can cancel out, right? So this 0 now can, meaning we're 0.4 meters away instead of 4. Does that kind of make sense? Okay. So with this, with a catapult, you actually have to apply a much, much larger force to our object here than what the force is here. Good? Any questions? No? This is why a lot of times you don't see catapults firing off huge things. Most of the time they're rocks, maybe a little bit smaller than like a cannonball. Yeah. Yes. Cool? You guys have any questions? No? All right. We're actually making really good time. I'm not used to having regular schedules. Do you guys have any questions on this? No? All right. I'm going to end the live stream here for the moment. Just, I can let them see that. Hello.